Well, hello everyone and welcome to lecture 9. We've been looking in some detail about phase diagrams, and we've looked at different examples of phase diagrams. So we've looked at unary phase diagrams, and we've had a look at binary phase diagrams, and we've had a look at quite a simple system known as the copper-nickel system. Now, what I want to do today is move on and look at some slightly more complicated versions of phase diagrams and have a look at something called a eutectic phase diagram. So let's have a look at this system here. It's another important binary phase diagram, and it's known as a binary eutectic phase diagram, and we'll see why that is as we progress. But we'll start by having a look at some of the common features between this and the phase diagrams that we've been studying so far. So the common themes here, well, there's an alpha solid solution. If you look right over to the left of that phase diagram, there is an alpha solid solution that's rich in copper. And that is a single homogeneous phase that's composed of the alpha copper as a solid phase. If you look to the right-hand side of that phase diagram, you'll see that there is a beta solid solution that is also rich in silver. And this is a single homogeneous phase composed largely of silver. You'll also see that there is a liquid region. There's a liquidous line. It looks a little different in shape to the copper-nickel system that we were looking at, but nevertheless there is a liquidous line there. It's kind of a V shape, and the point of the V hits this flat line, and we'll talk about what that is in a moment. But again, there is a single phase region for the liquid phase. And above that V-shaped liquidous line, the system is in a homogeneous liquid phase. Now, one thing that you'll notice is that as you add silver to copper, you decrease the melting point of the alloy. So have a look at my red arrow there and follow that line down. You reach a minimum in the melting point. That is the point at which liquid transforms into a solid, or vice versa, which is the melting point. Similarly, you'll notice that as you add copper to silver, you also decrease the melting point of the alloy. And at some point, both of those liquidous lines meet at this point E. This point E is known as the eutectic point, and it's designated by the eutectic composition and the eutectic temperature. And the eutectic temperature is that flat isotherm line. So the flat line on that graph that runs parallel with the x-axis is known as the eutectic isotherm, but the eutectic point is where that V meets. Now, this is a special point in the phase diagram of copper and silver because it's an important reaction happens if you are at the eutectic composition and you cool the mixture from a liquid. So look what happens here. As you cool the mixture from a liquid is transformed into two solid phases, an alpha solid phase and a beta solid phase. And you can see that below that line, you enter this two-phase region. But that two-phase region is composed of two solid phases. And we can show that reaction through the schematic shown here. So you go from a liquid phase that has 71.9 weight% silver to two solid phases, an alpha solid phase that has 8 weight% silver and a beta solid phase that has 91.2 weight% silver. Now, it's possible to conduct exactly the same kinds of calculations that we've been looking at for the copper-nickel system and other previously studied phase diagrams with these binary eutectic systems. So I show you a different binary eutectic system here. That is the lead-tin isotherm. And all I've done here is plot temperature against the weight percentage of tin. And we can work out exactly the same things. So we can work out the phases that are present, the composition of each of those phases, and the relative amount of each phase. So let's do that for the lead tin system. Let's imagine we have a 40 weight percent tin system and therefore a 60 weight percent lead alloy, and that is at 150 degrees Celsius. And let's try and calculate first the number of phases that are present. Well, we draw our coordinates. We draw lines that correspond to both the temperature and the composition. And in this case, that's 150 degrees Celsius and 40 weight percent tin. So we've got our coordinates, and we know that we are in that two-phase region, which is composed of an alpha and a beta solid. We can also work out the phase compositions. So in this case, I'm going to draw my tie line at my specified temperature, 150 degrees Celsius. And I'm going to drop perpendiculars to read the composition of each phase. So here I have an alpha phase, which is composed of 11 weight percent tin, and a beta phase, which is composed of 99 weight percent tin. And finally, I can work out the percentage fraction of each phase. So here I take the length of the tie line from the overall alloy composition to the phase boundary for the opposite phase. So if I'm trying and divide that by the total length of the tie line. So if I'm trying to work out the percentage fraction of the alpha phase here, then I take the length of the tie line from the overall alloy composition, which is 40 weight percent tin, to the phase boundary for the opposite phase. So this, I would take the length of the tie line from the overall alloy composition to the beta phase, which is 99 minus 40, and I divide that by the total length of the tie line. And that gives me an answer. So I have the relative amount of alpha phase that I have is 0.67 or 67%. And I can do exactly the same for the beta phase, so it's exactly the same calculation, but this time I take the length of the tie line from the overall alloy composition, 40, to the phase boundary for the opposite phase, so the alpha phase. So that now becomes 40 minus 11 divided by 99 minus 11, which gives me a percentage fraction beta phase of 0.33 or 33%. Clearly, when you've got a two-phase system, both of those numbers should add up to 1 or 100%. So if you don't get a number that adds up to 1 or 100%, you know you've done something wrong. Let's try another one, because we've got a couple of other two-phase regions in this, this phase diagram. Let's imagine that we have a 40 weight percent tin at system at 220 degrees Celsius. Let's first of all try and work out the number of phases that are present. Well, there are two phases present at this temperature and composition. There's an alpha phase and a liquid phase. I can work out the phase compositions. I can draw my tie line at the specified temperature. I can drop the perpendiculars, and I get an alpha phase which has 17 weight percent tin, and a liquid phase this time that has 46 weight percent tin. And I can work out the percentage fraction of each phase. So I can take if I'm trying to work out the percentage fraction of my alpha phase, I can take the length of the tie line from the overall alloy composition, in this case 40%, to the phase boundary for the opposite phase, in this case the liquid phase, and I get a percentage fraction of alpha phase as 0.21 or 21%. And again, I can do exactly the same for the liquid phase, and this equals 0.79 or 79%, and you'll notice now that both of those numbers add up to 1 or 100%. Now, the development of microstructure in these systems is really interesting because of the presence of this eutectic isotherm. So we'll stick with the lead-tin phase diagram, and depending on the composition of the alloy, we can get the development of some very interesting microstructure as we cool the alloy. And it's really important that we understand something about its microstructure as it's cooled, because the final microstructure can have a very, very big influence on the mechanical properties of the final material. And that's very, very important from the perspective of perhaps solid state physics, or from the perspective of engineering, because it's very, very important that we understand lots about the mechanical properties of the materials that we're going to use, especially from an engineering perspective, if we're going to put those to use in a building, for example, or any kind of load-bearing material. So cast your eyes back to the lead-tin example here. I show you a condensed form of the lead-tin phase diagram. And let's imagine the simplest case. So we just cool a composition with a very, very small amount of tin, so 2 weight% tin. All we do here is we cool from the liquid phase, so point A on the dashed line on the diagram there, through to an alpha solid phase. So we just very simply solidify a material from a liquid phase through to a single phase region. Now, compositions that range between the room temperature solid solubility limit and the maximum solid solubility limit of the eutectic isotherm, that is, they don't pass through that flat line, the eutectic isotherm. These start off in the liquid phase, so follow the red circles and the dashed line here. When you cross that first liquidus line, you get the nucleation of alpha phase solid particles. Cooling that further leads to all alpha phase particles. And cooling further still, you actually enter a two-phase region. You exceed the alpha solubility limit and beta particles start to form. So you get a sort of sea of alpha phase with small beta particles forming. Now, what about if you cool the material bang on that eutectic composition? So we come down through the V in the liquidus line past the eutectic isotherm, which is the flat line. So the eutectic composition is 61.9 weight% tin here. Well, we start off again in the liquid phase, and there are no changes that occur until we reach that eutectic temperature, and we pass through the liquidus line. When we get there, the system undergoes that eutectic reaction, so two liquid phases transform into two solid phases, an alpha solid phase and a beta solid phase. And we could read the compositions of each of those alpha and beta solid phases, and they're dictated by the eutectic isotherm endpoints. So we've got an alpha solid phase with 18.3 weight% tin and a beta solid phase with 97.8 weight% tin. Now, one thing you'll notice is that the composition of the alpha and the beta solid phases is completely different to the parent liquid phase from which it's cooled. There's a liquid phase there with 61.9 weight% tin and an alpha and a beta solid phase with very different weight percentages of tin. Now we know this is because of some kind of redistribution of lead and tin through atomic diffusion as the system cools and the system is trying to readdress that upset in equilibrium. And actually, the resulting microstructure that you get consists of these alternating layers or lamellae of alpha and beta phases. And you can see a micrograph of the eutectic transformation on the bottom there. What happens is that as a solid phase starts to nucleate, at the solid liquid interface, diffusion occurs that is just ahead of that interface. And lead atoms will diffuse towards the alpha phase, which is rich in lead, and tin atoms will diffuse towards the beta phase, which is rich in tin, and you get the evolution of microstructure with this lamellar appearance. So what about any other compositions that pass through that eutectic isotherm? Well, let's imagine we cool from the liquid phase through the eutectic isotherm to the left of the eutectic point. So that's the dashed line that you can see there. We start with the liquid until we cross that liquidus line and we enter the alpha solid and liquid phase region, and we start to get alpha solid phases that nucleate. Now, as you lower the temperature to a temperature just below the eutectic point, you start to get those eutectic structures evolving. So what you have is a system in which you've got that classic lamellar eutectic structure, but also alpha phases that have started to solidify as they pass through that alpha plus liquid phase region. So you can see you've got round alpha phases within a eutectic structure. So we call that the primary phases are the alpha particles, and you've got what we call a eutectic microconstituent. If we cool to the left of the eutectic invariant point, we call that a hypoeutectic system. If we cool to the right of the eutectic invariant point, we call that a hypereutectic system. And of course, in this case, we have beta particles as the primary phase and a eutectic microconstituent, as opposed to the hypoeutectic system when we have alpha particles as the primary eutectic phase. Sorry, it's the primary phase. So the copper nickel, the copper silver, and the lead tin phase diagrams are quite simple. They only have two solid phases, and they've got these terminal solid solutions that exist at either side of the phase diagram. Now, for the exam, I only need you to know about these phase diagrams. I will only ever ask you about the copper nickel, copper silver, and lead tin. But I do want to show you an example of and the iron carbon phase diagram, but we're going to come on to that. I want to show you an example of a phase diagram that is a little bit more complicated than these. So this is the copper zinc system, and I'll never ask you about the copper zinc system, but you can see it's a little bit more complicated, right? There are 6 different solid phases that exist here. There are 2 terminal solid phases that are found at the concentration extremes. There are 4 intermediate single homogeneous solid phases. You will notice some common points. There is a eutectoid invariant point, which consists of one solid phase that transforms into 2 other solid phases. There is a pereutectic reaction, which is when, upon heating, one solid phase transforms into a liquid phase and one other solid phase. Now, something that we do need to pay very special attention to is the iron-carbon system. And that's because steels and any cast iron are all iron-carbon alloys. So of all the phase diagrams we look at, the iron-carbon phase diagram is probably the most important. And that's because we build so many things out of steel and cast iron. So the steel cast irons are the primary structural material in every technologically advanced culture. So it's very important we understand something about that phase diagram. It's very important that we understand the microstructure that develops as we cool these materials, because ultimately that will dictate their mechanical properties. So here is the iron-carbon phase diagram, and we'll start very simply and imagine we have just iron, so no carbon added at this point. When we heat iron, pure iron, it experiences two changes in crystal structure before it melts into a liquid. At room temperature, iron exists in the ferrite or alpha iron phase with a body-centered cubic crystal structure. At about 912 degrees Celsius, it undergoes a polymorphic transition to a face-centered cubic austenite or gamma iron structure. And at 1394 degrees Celsius, it reverts back to a body-centered cubic crystal structure, but this time it's in the delta ferrite or delta iron phase. And finally, at about 1540 degrees Celsius, it melts. Now, what you'll notice is that for my iron-carbon system, that composition axis only extends to 6.7 weight% carbon. And that's because after 6.7 weight% carbon, an intermediate compound, iron carbide, forms. So we divide the iron-carbon system up into two distinct parts. From 0 to 6.7 weight% carbon, there is an iron-rich portion. This is the portion that we're interested in because all steels and cast irons have a carbon content that is less than 6.7 weight%. Above that, we're not interested in this for the moment. That's the carbon-rich portion that consists of 6.7 to 100 weight% carbon. So we're only going to consider the iron-rich portion. So that's the phase diagram that we need to be worrying about, the one in front of us. You'll notice that there is a eutectic point on that phase diagram. It happens at 4.3 weight% carbon and 1147 degrees Celsius. And here a liquid changes into two solid phases. So liquid iron changes into austenite and a cementite phase. There is also a eutectoid invariant point that happens at 0.76 weight% and 727 degrees Celsius. And here, upon cooling, a solid phase is transformed into two other solid phases, ferrite and cementite. Now, you can produce various microstructures in steel alloys. And the microstructure that develops is dependent on the carbon content and the heat treatment. And this is really, really important because what it means is that by changing the percentage of carbon and by changing the heat treatment, i.e. the temperature we heat steel up to and the rate at which we cool it, we can dictate the microstructure of the final material. And the microstructure has a profound impact on the mechanical properties of the material. And that's what, as engineers, physicists, that's what we aim to do, is tailor the microstructure to yield the mechanical properties that we require for the job at hand. So we are going to deal with, at the moment, the very slow cooling of steel alloys in which we maintain equilibrium. So let's consider a steel alloy of eutectoid composition, 0.76 weight% carbon, and that is cooled from 800 degrees Celsius. We're in the liquid phase initially, and nothing happens until we reach the sorry, we're not in the liquid phase. We're in the austenite phase, and nothing changes until we reach 727 degrees Celsius and we hit that eutectoid invariant point. At that eutectoid temperature, that austenite phase will transform into ferrite and cementite, and this is known as pearlite. And the microstructure here consists of alternating layers or lamellae of ferrite and cementite. And the layers form here because the composition of that parent phase differs from the composition of the product phases, right? So the austenite phase differs in composition to the ferrite and cementite phases. And we know and have looked at an example of this. The phase transformation requires that carbon is redistributed here by diffusion in order to maintain equilibrium. So carbon diffuses away from the ferrite and to the cementite regions. Now, in the same way that we can get hypoeutectic and hypereutectic alloys, we can also get hypoeutectoid alloys. So let's cool the same. Let's cool down through the eutectoid isotherm. Initially, we start in a phase whereby the system is entirely in the austenite phase. We cool into that austenite and ferrite region, and ferrite grains begin to grow and nucleate within the austenite phase. If we cool further, the ferrite grains grow very large. And as the temperature is now lowered to beneath that eutectoid isotherm, the austenite then transforms into pearlite. So then there are now two different types of ferrite present. There's the alpha phase that formed above that eutectoid isotherm, and there's the alpha phase that formed upon passing down through that eutectoid isotherm. Similarly, then, we can get hypereutectoid alloys. These are analogous to the phase transformations of hypoeutectoid isotherms, except that we now have cementite instead of we have cementite here. Okay, so we've looked at phase diagrams. We've said that they are useful tools for determining the number and types of phases that are present, the composition of each phase and the weight fraction of each phase. We've said that the microstructure of an alloy depends on its composition and the cooling rates, and we've only looked at equilibrium examples so far. And we've looked at some important phase transformations such as the eutectic, eutectoid and pereutectic.